How do you communicate with a volcano? For a long time, humans have tried to establish some kind of two-way relationship, to have two-way communication with volcanoes. Still today, some communities will regularly give offering in the form of flowers, meals, even animals to volcanoes in an attempt to appease them. But as history taught us, volcanoes don't care. There is no two-way communication possible. All we can do is listen. But here's the problem. Volcanoes, for most of their lifespan, are gentle, peaceful giants. The surrounding are fertile land. Their summits are beautiful summits to climb, making them touristic hotspots. And they're really quite nice place to live in. But every once in a while, they will explode violently. This can have consequences that are fairly local. Local pollution of air quality, pollution of the groundwater system, maybe the closure of local airports, all the way to catastrophic. Destruction of entire cities, impacting the climate of the whole planet for years. But as we said, all we can do is listen. So our role as volcanologists is to be interpreters, really. Is to look at the signals that we can get while the volcano is still in the quiet state in order to predict when it will erupt. How big is the eruption going to be? How long is the eruption going to last? I am an interpreter for volcanic gases. I look at volcanic gases and try to interpret what information they contain and what they can tell me about the state of the volcano and what is about to come. And so there are two parts to that. The first part is to go to active volcanoes and to start studying, measuring the signal that we get there, measuring the composition of the volcanic gases that are emitted from the volcano. When we can, we try to leave instruments that can measure the signal continuously over time. But you have to realize that some of these volcanoes are quite remote. It can take days to climb to their summit, sometimes hours to upsell down their crater. But for this type of measurement, you always need to get close. So close, in fact, that you can feel the heat on your face, that you can smell and even taste the nasty flavor of sulfur, that you feel the ground constantly shaking under your feet, that once in a while you hear an explosion so loud it'll make you jump back in fright, and that you'll end most days in the field completely covered in ash from head to toe. Ash gets everywhere. But measuring this signal is only half of the work. The other half is to interpret it. Now, to do this, while we're in this field, we're also going to collect lava coming out of the volcano. So we're going to take these pieces of lava and bring them back into the laboratory. In the laboratory is our practice volcano. We have special furnaces that can recreate the condition of extreme pressure and extreme temperature that exist inside of a volcano. And so we can recreate magma. We can create magma under controlled conditions and look at the effect of different parameters: pressure, temperature, composition of the magma, amount of water, sulfur, CO2 that is in the magma. A quick lesson in volcanology before we continue. The red rivers of molten rock that you see coming out of volcanoes, this is what we call lava. This same lava, when it's still inside the volcano, under pressure, we call it magma. Both lava and magma, if you cool it slowly, is going to crystallize and form minerals. If you cool it quickly, however, it's going to quench into a glass, which retains both the structure and the chemical information of the magma while it was still in its molten liquid state. In the laboratory, at our practice volcano, at the end of each experiment, we're going to cool the experiment extremely quickly. And so we're going to freeze the magma into a glass like the one you see here. And so we can analyze both the composition of this glass and the composition of the gas phase, which you see in these bubbles, that coexist with the magma in the pressure temperature of interest. And so we do this one experiment at a time. And little by little, what we're creating is basically we're trying to understand what gas composition corresponds to what magmatic conditions. And so little by little, we're building a kind of Rosetta Stone that will allow us to interpret volcanic gas chemistry in terms of magmatic conditions. I'll show you an example. This is Mount Villarrica in southern Chile. The picture you see is the paroxysmal phase of its last eruption in 2015. The column of lava that you see is 1 kilometer high. And you have to imagine that this volcano, in quiet time, is actually an extremely popular touristic place. Very popular summit to climb, very popular ski resort in the winter. And so at this volcano, the composition of the volcanic gases has been measured routinely. And an interesting thing that we discovered that prior to the eruption, a few months prior to the eruption, there was a change in the composition of the gas emission. An increase in the amount of CO2 compared to the amount of sulfur dioxide that was emitted. This is a signal that comes out of the volcano. But this signal by itself really doesn't tell you much. Now, thanks to all the laboratory experiments, thanks to all this Rosetta Stone that we've been building piece by piece and that we continue to build on, we're able to interpret this signal now. In this particular case, it means that there was an increase in the contribution of deeper magma at around that time. And so we could see that the deeper magma was kind of coming into the shallower reservoir. So 2 months prior to the eruption, we could tell that magma was in motion. Magma was coming up from depth. If we listen to the signal, and if we interpret the signal, we can forecast eruptions to come. This is Mount Nyiragongo volcano in the Democratic Republic of the Congo during its eruption earlier this year. And here's what happened when no one is listening. 7 months prior to this eruption, all fundings to the local volcanic observatory had been cut. So no one was listening to the volcano, let alone trying to interpret anything. What you see in the foreground is the city of Goma. 700,000 people live there. Evacuation started in this city as the lava was starting to enter people's home. The evacuation was chaotic. 32 people were, well, 32 confirmed casualties, hundreds of people still missing. This is Comble de la Vieja volcano in the Canary Islands, an eruption that started just last month and is still ongoing at the time we speak. And here's what happened when somebody is listening. It's a very similar type of eruption as the one we just saw. It's very fluid, basaltic lava. But here, the volcanic observatory was listening and was interpreting the signal correctly. So 1 week prior to the eruption, everybody in this area had been contacted by the local authorities, had been told to start packing and prepare for an evacuation to come in the next few days. A few days prior to the eruption, local authorities evacuated people with reduced mobilities, and a full evacuation order was given just prior to the eruption. The evacuation happened calmly. There were no injuries, no casualties. The eruption still happened, though. There's now thousands of houses that have been destroyed. If you look at pictures of this place now, it is complete ruin. It is very sad, and what's very sad that there's nothing we can do. Because you see, we cannot stop a volcano from erupting. But if we listen to the signal, and if we interpret these signals correctly, we can at least forecast when it will erupt and step out of the way, at least momentarily. Thank you very much.